Hi guys, in the last lecture we started with power electronics. We saw what is power electronics, what are its applications in respect to machines, power system, transportation, renewable energy sources. Then we saw the advantages, in which the biggest advantage with power electronics was that it has high efficiency of conversion. Then we saw disadvantages, in which the biggest disadvantage was harmonics introduced by the power electronic converters. Then we saw Fourier series, which is a prerequisite for the power electronics course, and we derived Fourier series for certain waveforms that are commonly encountered during this course. In this lecture what we will do is we will be starting with the power semiconductor devices, which is our first unit for the power electronic course. Okay. Now what are power semiconductor devices? Power semiconductor devices are the solid state electronic devices which are designed to operate at high values of voltages and currents. Okay, or which are designed to operate at power ratings. So these are solid state devices. Solid state electronic devices which operate at high rating. Some of the devices in this category are power diode, then thyristor family, similarly transistor family. Now what is the speciality about the power semiconductor devices is they are designed so that we can control their operation to change the form of power, that is from AC into DC or DC into AC. We can control their turn on and turn off so that we get a controlled output. So we wish to control their turn on and turn off. Now these devices are always designed to operate as switches. In power electronics, whenever we wish to change the voltage or any parameters of the power, then we need switches. So these are designed to operate as switches. Like in BGT, when you study, there are three regions of operation: cutoff, active and saturation. In active mode it acts as a amplifier, and in the other two modes, cutoff and saturation, it acts as a switch. In saturation it is in the on state, in cutoff it is in the off state. Similarly here all power electronic devices will be designed to operate as switches. Now if we are designing any device to operate as a switch, then we must understand what is the ideal switch or what is the ideal characteristics of any switching device. Now when we talk of ideal switch, these are the switches that we generally encounter in the circuits. Like in case of network, whenever we do transient analysis, we consider certain switches. Let us say a switch is closed at t is equal to 0, find the current. Such sort of switches are ideal switches. Now, what are the characteristics of ideal switch? When the switch is on, okay, when you close a switch, then its voltage is 0 and the current can have any value. When the switch is closed, it is called to be in the conduction state. In conduction state, voltage drop is 0 and current can have any value up from minus infinity up to infinity. Okay. Now if we want to find the power of the switch, which will be equal to V on into I on, it will come out to be 0. This is called as your conduction loss. Okay, that means the loss of power in the switch when it is in the conduction state. So for ideal switch, conduction loss is 0. Now when the switch is open, in such a case the switch must not carry any current. So I off will be 0. And the voltage across the switch will be determined by the supply and the load, and it can have any value. Okay. So if we wish to determine P off, it will be V off into I off, that is 0. This is called as your blocking loss. Off state of the switch is also called as blocking state. So blocking loss must also be 0. Now when we study about switching of these sort of switches, we say that switch is turned on at t is equal to 0 or turned off at t is equal to t naught. That means the switching is instantaneous. Okay. So change of state is instantaneous. That means turn on time and turn off time both must be 0. So the switching time must be 0, due to which switching frequency is infinite. Now switching frequency being infinite means you can apply signal of any frequency at the terminals of this device. No matter what is the frequency of that signal, this device can be able to handle, because its limitation is the infinite frequency. The next property of ideal switch is it does not require any energy to turn on and turn off. That is, energy of turn on and turn off both is 0. Otherwise, what happens is, suppose we talk about BJT. In case of BJT, if it is acting as a switch, then also we need to apply base current to turn on and turn off. So we need to supply some power by means of biasing. But in case of ideal switch, we need not have any external source to supply the power to change the state of the switch. And the last property is it is stable under all operating condition. Okay. That means doesn't matter what is the value of voltage and current across the switch, its operation will be stable. Now let us understand how a practical or a real switch differs from this. Now the first assumption in ideal switch was there is 0 on state voltage drop and the current can have any value. But in a practical switch, on state voltage drop is non-zero and the current can vary between certain minimum to a maximum value. Okay, like in case of diode. Now the thing is, on state voltage drop usually in case of analog electronics we take as 0.7. So on state voltage drop is non-zero and the current can vary from 0 to infinite. And as you keep on increasing the current at certain point, what will happen is the heat produced in the switch will be very high, due to which it can get damaged. So there will always be limit even on the maximum amount of current that can flow in the device. Okay. Higher current implies higher power means higher heating. In the next assumption I said that when the ideal switch is opened, it carries 0 current and it can have any amount of voltage. But consider a diode. When it is off, it carries a reverse saturation current. That means off state current is always non-zero and voltage can vary between certain minimum and the maximum value. Why? Because suppose if you keep on reducing the voltage and you go below the breakdown voltage, then the diode will break down and it will start conducting. Similarly, if you go above the knee voltage, then also it will start conducting. So we have a limitation on the minimum and the maximum voltage. The next assumption was it can turn on and turn off instantaneously. But here turn on and turn off will require certain time. So let me give you an example in reference to diode only. In diode, during the on state or during the forward bias state, the depletion width is small. Now depletion region, what does it indicate is the region in which there are no charge carriers. But in off state, depletion width is high, that is the region where there are no charge carriers is large. Now to increase the width of such a region, we need to remove the charge carriers. And if you need to remove the charge carriers, then you need certain time. That is how adding or removal of the charge carriers requires certain time, due to which on and off time are finite but non-zero. Due to which switching time is non-zero and switching frequency is finite. Now suppose switching frequency comes out to be 100 kHz. So it defines the maximum frequency that can be applied across the device. You cannot go beyond the 100 kHz, otherwise the device will not be able to work properly because time will be lesser. So before it is even turned on, you will be starting to turn off the device. Then the operation will not be proper. Now the next assumption was that it does not require any energy, but here E on is not equal to 0. Similarly, E off is not equal to 0. Now, from where does it get this additional energy to turn on and turn off? It gets it in the form of drive circuit. With power electronic switches, we will apply drive circuit from where it will derive the power to turn on and turn off the device. And the last condition was stable under all operating condition, but here we will have certain thermal limit. That is, you cannot apply any amount of current, otherwise the losses will be high, heating will be high and device will melt down. To remove the heat from the device, we make use of the heat sink. Okay, that is why all power electronic devices are mounted on the heat sink so as to remove the heat generated in the device. Now let me draw the characteristic of ideal as well as practical switch. When we draw characteristics of switches, we consider two characteristics. One is the switch voltage, other is your switch current. Now suppose initially the switch is off. If the switch is off, then there will be certain voltage across the switch. When the switch is off, there will be certain voltage and the current will be 0. Like this. We are now talking about the ideal switch. As soon as you turn on the switch, the voltage will go to 0 and the current will become high. Like this. Then we again turn off, then voltage will again become high and current will again become 0. So this is the on state, this is the off state. So remember, in the off state the voltage is high, in the on state current is high. Now what about the practical switch? In practical switch, when it is in the off state, the current will be non-zero. Let me take another color. It will be non-zero and the voltage will be high. Now when you start it to turn on, then voltage will decrease gradually and current will also increase gradually. This time will be called as your turn on time. Okay. Now it will remain at a lower value but not 0. Current will remain at a higher value. Then again when you turn off, voltage will increase gradually. Similarly, current will also decrease gradually. So this is called as your turn off time. Okay. So for the practical switch, in the off state and on state, current and voltages both are non-zero, and during the switching it takes a finite amount of time. Similarly, when we talk about the stability condition, for an ideal switch it is stable under all operating condition. That means on the VI curve it can operate anywhere. Okay, any point is a stable operating point. But for a real switch, there will be limitations on the maximum and minimum voltage, similarly maximum and minimum current. Also there is a thermal limitation, that means Pmax, which will be equal to V into I, should be constant. We cannot exceed Pmax. That means Vi is constant. Curve will be a hyperbola. So at the edges it behaves as a hyperbola. Okay. So the region inside this is called as SOA, which is the safe operating area. So for a practical switch, safe operating area is finite. For a ideal switch, safe operating area is infinite, which consists of all the 4 quadrants entirely lying in the SOA. Okay. So if all the 4 quadrants lie in the SOA, that means you can operate at any point on the curve and the operation will be stable. Now let us understand what are the various categories of switches. Okay. So the first category is based on type of control. How much control you have over the operation of a switch. The first type of switch is called as uncontrolled switch. Now in uncontrolled switch, we cannot control the switching on and switching off of the switch. That will depend on the supply. Means by application of any external signal, I cannot control whether the switch is in the on state or in the off state. That will entirely depend on the supply and the load. An example of this is diode. Now, when you apply a forward bias across the diode, that is VAK greater than 0, then it turns on. But there is no third terminal in the device which can be utilized to turn on and turn off the device. Similarly, when VAK is less than 0 and IA is not equal to 0, device is on, and if IA is equal to 0, device is off. Okay. So that is the characteristic of the diode. So it is a kind of uncontrolled switch. Which of the switches will be uncontrolled? Wherever you do not have a third terminal to apply the control signal to turn on and turn off the device will be called as uncontrolled switch. The next type of switch is called as semi-controlled. Now in semi-controlled type of switch, what happens is you can only control one state. That means either you can turn it on or you can turn it off, but not both. So one switching state is in my control, other switching state I cannot control. Those sort of switches are called as uncontrolled switch. What is an example? SCR. Here we can control the turn on by gate signal, but turn off will depend on supply, like the case of diode. So during turn off, it just like behaves as a diode, so turn off is uncontrolled. So those sort of switches are called as your semi-controlled switches. And the last category will be fully controlled. In fully controlled, we can control both the switching states of the switch, that is turn on as well as turn off. So here both switching states are controlled. Example, GTO, which is your gate turn off thyristor. Here the gate signal can be used to turn on as well as turn off the device. Then transistors. No matter what is the type of transistor, whether it is BJT, FET or IGBT, all are fully controlled type of switches. Okay. That means by application of control signal, you can turn on and turn off the device. So this is the first classification of switch based on whether or not you are able to control its operation. The next classification of the switch comes on the basis of what is the polarity of the blocking voltage and what is the direction of current flow through the device. Now first category in this comes as unipolar switch. Now unipolar switch means that the switch can block only one polarity of voltage. That means if you apply the other polarity or the other direction of the voltage, then it will turn on and will start conducting. So it can stay off only for a one polarity of voltage. Like in case of diode, if we apply negative voltage, then it can stay off, but as soon as you apply positive voltage, it will turn on. So we show characteristics like this. How do we show this? That means up to this point, the current is 0 and the voltage is variable. Or you can show something like this, a solid line here. So it shows that for voltages up to from 0 up to VBR, current will remain 0. And since this point is shown as finite point, it means it is a real switch. For a practical switch, this entire negative x-axis will lie in the characteristic, okay, because the breakdown voltage will be infinite. So that is the case of unipolar switch. Similarly, if it blocks positive voltage, then what will be the characteristic? Like this. So that is the case for a transistor. Usually the reverse blocking capability in the transistor is very low, so they can block forward voltage until you apply a gate signal or a control signal. When you apply the control signal, then this device will turn on. Similarly, next type of switch is your bipolar switch. In bipolar switch, what happens is it can block both polarity of voltage, positive as well as negative. An example of this is SCR. In negative, it behaves as a diode. In positive, it will block until you apply gate current. Until gate current is 0, it will stay off. So that is how it blocks the positive as well as negative voltage. Without the application of gate current, it won't turn off below this voltage. But as soon as you apply gate voltage either you apply a voltage higher than this or you apply gate current, it will turn on. Okay. So that is the characteristic of the bipolar switch. Similarly, based on direction of current, we classify as unidirectional switch, which means it carries current in only one direction. So characteristics will be like this, because when we talk about the on state of the switch, we consider the voltage drop as 0. So when it is conducting, it will lie on the y-axis, so that voltage of the switch is 0. This is I, this is V. What is the example diode? It can only carry current from anode to cathode. SCR, anode to cathode. Transistors, they also carry current in one direction. So most of the devices are unidirectional. Similarly, the counterpart will be bidirectional. In bidirectional type of switch, it can carry current in both directions. An example of this will be triac. It is designed to have the bidirectional characteristics. So now let us see the characteristics of the power semiconductor devices based on this second classification. So first we take the case of a diode. Now based on the above classification, it is a unipolar and a unidirectional switch. So characteristics will have 2 points. This indicates the blocking state. This indicates the conduction state. So in ideal characteristics, we have to show both the blocking as well as conduction states. Now it is a uncontrolled type of switch, unipolar and unidirectional, and the safe operating area, that is the operating area of this switch, is this. This is your second quadrant. Okay, so that is how we determine the safe operating area between the current and the voltage limits. Now if we talk about the transistor, whether it will be BJT which has a base, collector, emitter, or it is FET, drain, source, gate, or it is IGBT, gate, collector, emitter. All will have same characteristics. Emitter, all will have same characteristics, that is, they will block one polarity of voltage and conduct current in only one direction. So it is a fully controlled type of switch, but it is unipolar and unidirectional, and the SOA will be first quadrant. Okay, so this is about the transistors. Next we see the SCR. How do we represent a SCR? Like this, 3-terminal device, anode, cathode and gate. It is a bipolar and a unidirectional switch. So characteristics will be like this. Okay, so it is a semi-controlled type of switch. It is bipolar and unidirectional, and the SOA will be first and the second quadrant. Next we talk about GTO. In GTO, we have like this. So here it is a fully controlled switch, but the characteristics remain the same. The only difference between SCR and GTO is that GTO can be turned off with a negative gate pulse, but SCR cannot be turned off by gate signal. Okay. Next we consider triac. Triac behaves like two SCRs in anti-parallel. So this is termed as main terminal 1, main terminal 2 and gate. Why main terminal 1 and main terminal 2? Because it is a bidirectional device. It can carry current in both directions. So we cannot define anode and cathode, because if we define anode and cathode, then current always flows from anode to the cathode. So that is why triac will be named as main terminal 1 and main terminal 2. So it is a bidirectional as well as bipolar switch. Okay, and its SOA will be all the 4 quadrants, and it is a fully controlled type of switch. That is your triac. Next we consider the characteristics of body diode. Now what is a body diode? It is a parasitic diode in certain devices. Now basically what is a diode? A diode is nothing but PN junction. So in certain devices a PN junction is formed which will behave as a diode, and it carries current in opposite direction as compared to the device. So those devices are MOSFET and IGBT. Since it carries current in opposite direction, it is shown in anti-parallel. Like this is your gate, then drain, then source, and then diode will be anti-parallel. Since this MOSFET will carry current from drain to source, this diode will carry from source to drain. It will carry current in this direction and MOSFET in opposite. So it becomes a bidirectional switch. Similarly, in case of IGBT, there will be an inherent body diode like this: gate, collector, emitter. So due to which the characteristics change, and they are now something like this: unipolar and bidirectional. So why it is unipolar is because whenever you will apply a negative voltage, that is whenever VC is less than 0, or we can say VEC is greater than 0, then what will happen is this diode will turn on and it will start conduction. That is why it can block only one polarity of voltage. So remember, whenever diode is connected in anti-parallel to any device, the device behavior will be unipolar and bidirectional. Like if we connect a diode in anti-parallel to SCR, by default SCR is bipolar, but whenever a diode is connected, it will become unipolar and bidirectional. So that is the purpose of the anti-parallel diode. In these two devices, this anti-parallel diode is inbuilt, but in other devices, you have to connect an anti-parallel diode in external if you want to have a bidirectional behavior. Now let us see a problem. We are given a switch. We need to know which of the following devices can be used. Now when the switch is open, voltage can be positive as well as negative. This indicates a bipolar behavior. And since current is shown in only one direction, it is unidirectional. So we need to find which of these devices is bipolar and unidirectional. This is my SCR. It is by default bipolar and unidirectional. Here BJT is shown with the anti-parallel diode. So the first thing is this is external diode. Do not think that it is body diode. In case of BJT, there is no body diode. So whatever diode is shown is externally connected anti-parallel diode. Now, due to this external diode, the characteristic will be bidirectional and unipolar. As I told you, it cannot block negative voltage because when you apply negative voltage, this diode will turn on and carry current in opposite direction. So it is bidirectional. What about this? This BJT can carry current in this direction. Diode can carry current in this direction. So it is unidirectional. Opposite current is not allowed by either BJT or diode. What about the blocking capability? When you apply positive voltage, it will be blocked by BJT, so it will stay off. And since both are connected in series, for the switch to turn on, both must be on. Whenever either one switch is off, the entire switch will be off. So it will block positive voltage. What about negative? This BJT won't be able to block negative voltage, but this diode will not conduct for negative voltage. That is, it will not conduct when the polarity is like this. So it will block negative voltage. Okay, so it is bipolar. For positive voltage, BJT will block. For negative voltage, diode will block. And for the device to turn on, both must be on. So whenever either one is off, device is off. So answer will be these two. Now suppose we wanted to make this switch bidirectional. How to do that? Remember, whenever you want to make any switch bidirectional, then you connect two such switches in anti-parallel. How to do that? You connect something like this. If you connect two switches like this, this is my control terminal C and power terminal A and B, then it becomes a bidirectional switch because one device will carry current in one direction, other in opposite direction. So to get a bidirectional behavior without changing the unipolar or bipolar, we connect two identical switches in anti-parallel. But if you want to have bidirectional and unipolar behavior, connect an anti-parallel diode. So let me summarize what we covered in this lecture. We first saw what is meant by power semiconductor devices, and I told you they operate as switches and not in the active mode. Then we saw what is meant by ideal switch and a real switch. We compared the characteristic of both. Then we classified the switches based on their control characteristics like uncontrolled, semi-controlled and fully controlled. Then we classified the switches based on unipolar, bipolar, unidirectional, bidirectional. And then we saw the characteristics of the power semiconductor devices based on their polarity and the direction of the current flow. So that is what we have covered in this lecture. In the next lecture, we will study about the losses in the switch and what are the classification of the devices. that we cover in the next lecture.